Okay, so when we condense logs, we're going to take the process of expanding and exactly go backwards. So if we look at a couple of examples here, we're going to have maybe the log base 4. Oops, let's not do 2. I wanted to do x there, actually. Let's get rid of that. Log base 4 of 2 plus the log base 4 of 32. And what we want to do is we want to condense this. And the reason that we might want to condense this, hopefully you'll see after we do this. If I was to look at this, I could actually figure out what the log base 4 of 2 is. That's an actual number I could get. I think it's a half if I'm not mistaken. But the log base 4 of 32, that's a little bit harder. 4 to what power would give me 32? That's not easy to figure it out. And remember, it's not multiplication, not 4 times 8 equals 32. It's 4 to what power? So 4 squared is 16. 4 cubed is 64. It's not easy to figure out what power that would be. So what we should do is we should condense this. We should take the process and go backwards. So if I have 2 logs being added, remember that that comes from one log which has 2 things being multiplied together. One major key: the bases must be the same to condense them. Okay, so this is going to end up being 1 log base 4, and because the 2 things here are being added, I'm going to re-put them back together as multiplication. So that'll be 2 times 32. Well, of course, I can do 2 times 32. That's 64. And now you just ask yourself, well, does this actually give me something that I can simplify? And it does, because 4 raised to some power gives me 64. Well, 4 to the 3rd power happens to be 64. So this simplifies to 3. And that's why we might want to be able to condense logs. There's other reasons that we're going to get into when we get to more algebraic stuff, but that's one of the reasons. Okay, the next one won't really simplify the same way to a single value, but it's going to work out that we want to be able to still simplify it. So we're going to have the log of 4x minus 3 minus the log of x, and we want to condense this. Basically, we want to put it, what condensing means, we want to get it down to 1 log. First of all, bases are the same. The bases are not written, so they are 10. No problem there. I've got a subtraction symbol in the center here, which means that when I put these together, I'm going to divide the arguments. So when I condense this to 1 log, it's going to be 1 log base 10, and then I will divide the arguments. Now remember, the one that's being subtracted goes on the bottom. The other one, which is not being subtracted, or if it's being added, it goes on the top. So the 4x minus 3 part goes on the top, and the x part goes on the bottom. That is condensed into 1 log. Nothing else I can really do to simplify that because I've got the variable in there. But that is a condensed log. Okay, let's try some more complicated ones now. Let's go with 1/2 log of x plus 4 log of, let's go with x minus 3. So I got 1/2 log of x plus 4 log of x minus 3. Now the steps here are going to be, again, this is completely in reverse from what we've been doing. I have things out in front of the logs now, so when I condense these, I need to make sure that I get everything in front of the log being multiplied up as an exponent. So I'm going to take it, I'm going to move this 1/2 as the exponent here of this x. I'm going to move the 4 as the exponent there of the x minus 3. So that's the first step. So we're going to have the log of now x to the 1/2 power. And then this one is going to be the log of x minus 3 all to the 4th power. Okay, now I've gotten the stuff away from the front of the logs. Now I can go ahead and condense these 2 things into 1 log. And again, these 2 things here are being added. So when I condense them, when I put them back into 1 log, now the 2 pieces, the arguments, are going to be multiplied together. So we're now going to have the log, or 1 log, of the first one times the second one. The first one is x to the 1/2, and I could technically leave it like that, but a 1/2 power is a square root, so I'm going to write that as the square root of x times x minus 3 to the 4th. Now that is all one log. It is condensed down into one log. And you could always double check yourself by going back and expanding it just to make sure it works. Okay, let's do a couple of more. Let's do 3 ln of x plus 7 minus the ln of x. Okay, again, first step, if you have anything out in front of your logs, bring them up as exponents. So we're going to bring that 3 up to the exponent of the x plus 7. So it'll be the natural log of x plus 7 cubed. Make sure you keep those parentheses. That's very important. Minus the natural log of x. Okay, so I brought the exponents up. Now what I need to do is condense the two logs into one. So I'm going to get one natural log, and because it's being subtracted, now the arguments will be divided. So I'm going to have x plus 7 cubed divided by x. And that is what I am taking the natural log of. That is condensed into one natural log. Okay, one more. Let's say we have 4 log of x base 6 minus 2 log of 6 base. Actually, let's make this base b. Let me get rid of that. I don't want to make it base 6 because that'll defeat my purpose here. Let's make it a b instead. Base b, and then minus 1/2 log of y, also base b. Okay, all the bases are the same, so we can condense these. First step, bring all of the coefficients, bring all of the things being multiplied out in front of the logs, bring those up as your exponents. So we're going to have the log of x to the 4th, base b, minus the log of 6 squared, base b, minus the log of y to the 1/2 power, base b. Okay, now I've gotten all of the exponents. Now I can condense everything into one log. So I'm going to have the log base b. Now, the first one here is positive, that log of x to the 4th. There's no sign out in front of it, so that means it's positive. It's understood to be a positive log. So it's going to go on the top. The second one is being subtracted, so that 6 squared is going to go on the bottom. But of course, 6 squared, we can do that. That's 36. So we're going to put a 36 down there. The second one is also being subtracted, so it goes on the bottom as well. And it's y to the 1/2. We know that the 1/2 is a square root, so we're going to write that as the square root of y. That is a condensed log. Log base b of x to the 4th, all divided by 36 square root of y. Okay, that is condensing logs. Okay, our last topic of this section is what's called the change of base formula. So this is probably more useful before calculators were as advanced as they are now. Nowadays, most calculators, you can actually enter in logs with different bases, and you can get a decimal approximation of your value. For example, if I wanted to do the log of 140 with a base of 5. 5 to some power is not easy to find when it comes to 140, because 5 cubed is 125, 5 to the 4th is 625. So finding 5 to the what power gives you 140 is not easy to do. So you can't simplify it that way. And if you were just to go to an older style calculator, typing in the log of 140 would give you a log with only a base of 10. That's the way the calculators used to work. Again, nowadays the calculators, you can actually plug in log of 140 with a base of 5, and it's going to give you the decimal approximation. But it used to be that that wasn't the case. So the change of base formula was useful because what that says is, and we're going to go in general here, if I were to have a log of m base b, what I can do is I can change the base to any base that I want it to be, and I can take the log of m with that new base, whatever it is, I'm just going to leave it as a base 10, and divide that by the log of b, which you notice was the original base, and that is exactly the same thing. Okay, and we can actually, you can actually attempt this in your calculator and see, especially if you happen to have a calculator that can do different bases. If I can pull it up on my calculator to show you, I will do so. But it doesn't really matter. I could write this as the log of m base 7 over the log of b base 7. These are all the same. What I have done by doing this specific little formula here is I have just changed the base to the same base no matter what. Well, it was helpful to use a base of 10 because this is what calculators could compute. So if I was going to do the one that we have on the left here that I started with, it would simply be the log of 140 divided by the log of 5. And the easiest way to remember that is this number right here, which is your base, which is the lower one, is always the one that goes on the bottom. And it doesn't become the base anymore, it becomes the argument of the lower log. So if you were to type log of 140 over log of 5 in your calculator, you would get a decimal approximation. And I just happen to have that one, and that's about 3.07. Again, I'm going to try and pull this up on the calculator to show you that this is the case, and we'll see that it works out. Oh, and the other thing is, because the logs can be any base that we want them to be, this whole thing over here could also be written as the natural log of m over the natural log of b, because the natural log has a base of e, so again, it's the same base. Any of these things work. Let's see if I can get this on the calculator and show you what I mean. Alright, so what I'm using here is I'm using the TI Nspire CAS edition on my iPad, and I'm going to show you that the change of base formula works. So we've got the log. Now this actually can do a specific base. Ours was the log of 140 base 5, so I'm going to enter the base of 5, and I'm going to enter 140. And again, we're going to see what this actually gives us. Whoops, I forgot I have to make it do the approximation here. So let's go ahead and copy that. Let's see, paste that there. That's kind of a cool feature. So let's give the decimal approximation here to this. So it is 3.07, which is about what I said it was in the previous part of the video. So now let's show that the actual change of base works. So the first thing I'm going to do is I'm just going to enter a log of, and I'm not even going to type the base in. Let's see if it works without typing a base in. Log of 140, and then we're going to divide that. Whoops, don't want the division symbol inside. We're going to divide that by the log of 5, because that's the change of base formula. And let's see if what it gives us. There it is, 3. It's exactly the same thing. It inserted the base 10, which is really kind of cool. Now let's show that I could put any base in there and it won't make any difference. So let's do the log, and I think I used 7 on the other one. Let's do log base 7 of 140, and we'll divide that by the log base 7 of 5, and it will give us exactly the same thing. There it is. And the last thing I want to show you is that it also works with natural logs. So if I separate this to be the natural log of 140, and I divide that by the natural log of 5, it will be exactly the same thing. There it is, very cool. All right, so basically that, I mean, that's not an actual proof, but it does show you, at least for these examples, this is going to work. This is what the change of base formula is. So it's the log of the argument divided by the log of the base. That will give you a decimal approximation. It is how you change the base.